Hello friends, this video on P block elements part is brought to you by examfear.com. No more fear from exam. Let's talk about some chemical property trends. We'll talk about the reaction with air, hydrates, reaction with water, halides. Let's start with the reaction with air now. See, the first property is all the members when heated with oxygen form oxides, monoxides and dioxide. For example, carbon, when you heat with limited oxygen, less oxygen, it forms carbon monoxide. You heat carbon with ample oxygen, it will form carbon dioxide. So it forms monoxides and dioxides actually. Oxides in the higher oxidation state are generally more acidic. So this one, if you see, it has +2 and this is +4. This guy is more acidic. The dioxides, if you see, are more acidic. If you see, these are more acidics, and these guys are amphoteric. So if you see, these guys are acidic, dioxides, and these guys are amphoteric. Why? Because seriously, these guys are metals and non-metals and metalloids, so they have acidic oxides and dioxide. And these guys are metal, so they have amphoteric or basic oxides, right? That's the reason. Because these are metals and metalloids, non-metals and metalloids, so they have acidic oxides. These guys are metal, lead and tin, so they have amphoteric or basic oxide. So if you see SnO2 and PbO2, they are amphoteric in nature. So if you see, if you go down the group, the basic nature increase. Basic nature of oxides, right? And this is similar to the trend we have seen in the boron family, correct? And if you see among monoxides, if you see, CO is neutral, GeO is acidic, and these are amphoteric. So if you see, the carbon monoxide is the only exception here. It is neutral. Why it is neutral? It has to be acidic, right? Going by the trend. But this is neutral because the triple bond is there, right? It's a very, very strong bond in carbon and oxygen. And that's why it is basic. It's very difficult to break this bond. The bond energy is pretty high. That is 870 kilojoule per mole. Because this such a high bond energy, carbon monoxide is the only exception here. Other oxides, monoxides also, if you see, has to be basic. So because going down the group, the basic nature increased, right? So if you see, this guy is acidic, correct. These guys are basic, amphoteric is correct. So going down, the basic nature increase, but the exception is carbon monoxide. It can be asked in exams also why carbon monoxide is neutral while other monoxides are basic. This is because the carbon monoxide bond is very strong and it's almost 870 kilojoule per mole. It's very difficult to break this bond. We'll talk about the resonance structure of carbon monoxide also. So if we draw the resonance structure of carbon monoxide, you have carbon 1, 2, 3, 4, oxygen you have 6, 1, 2, 3, 4, 5, 6. This is one structure. The other structure can be the carbon, you get 5 here because oxygen is giving 1 electron to carbon, oxygen gets a positive charge, carbon gets a negative charge. The other structure can be, they can share this 2 electrons, right? So this is carbon gets a positive charge and this is because the resonance, if you see the resonance actually is 3 different structures for carbon monoxide, and with resonance also it gets extra stability and it becomes. Let's talk about the hydrides now. So this carbon family elements, they combine with hydrogen to form covalent hydrides. Please note, they always form covalent hydrides. For example, alkanes, alkynes, alkenes, silicanes, amines. These are the examples of the hydrides you have, right? You have the CH4 is one hydride. These hydrides, if you see, the thermal stability of these hydrides decreases as we go down the group. And the tendency to form these hydrides also decreases as we go down the group because carbon forms more hydrides, maybe lead forms lead hydrides. Right? So if you see, right, all the hydrides of carbons are pretty stable, methane and all, but the lead hydrides are pretty unstable. So you can say that if you go down, the stability of hydrides decrease. And since the stability decrease, it's very rare to form hydride as you go down the group. Let's talk about the reaction with water. Carbon, silicon, germanium, they are not impacted with water. But the tin, carbon, silicon and germanium is done. But talk about the tin. Tin will react with hot water, that is steam, to form dioxide and gives dihydrogen gas. So this tin reacts with hot water to give dioxides and dihydrogen gas. And with lead also, it forms a protective layer. Similar to aluminium, the lead, when it reacted with water, it immediately forms a protective oxide, and which helps helps lead in saving itself. It won't react with water then. Let's talk about the reaction with halogens. So most of the elements in the carbon family, they form halides. The formula MX2 or MX4, because oxidation state is +4 and +2, right? So they form generally MX2 and MX4 directly when react with halogens. But carbon is something which doesn't react directly. It forms halide but doesn't form halide directly. And most of these halides are covalent in nature. And these central atom in this halide, the carbon family atoms, they generally go sp3 hybridization, except these values because they are ionic. But since they are MX4, right, so they generally go for sp3 hybridization. And the stability of these halides increases as we go down the group. Stability of dihalides I am talking about. Why? Because as we go down, the +2 oxidation state is more prominent, right? So the stability of dihalides increase. For example, if you see lead chloride is more stable than lead PbCl4, right? Because the dihalide stability increases as we go down the group, because the +2 oxidation state is more stable as we go down the group because of inert pair effect. For example, in this, right, PbX2 is more stable than PbX4 because lead stable. But if you talk about germanium, then GeX4 is more stable than GeX2 because Ge +4 is more stable, and for lead +2 is more stable. That's why we see in the lead PbX4 is more stable than PbX2 is more stable than PbX4, but in case of germanium, +4 is more stable than +2. Let's talk about the hydrolysis of halogens. So except CCl4, other tetrachlorides we have, PbCl4 or something, they easily hydrolyze with water. Because the central atom can accommodate lone pair of electrons from oxygen. But since the carbon is small in size, it cannot accommodate, right? But other than, for example, SiCl4, right, this can accommodate the lone pair from hydrogen water, and it can, you see, this will replace the chlorine molecules with OH. And if you replace one by one all, you get this acid. Correct? So CCl4 is not able to hydrolyze because the carbon size is small, and it will not be able to handle this OH molecules, the bigger in size, right? So as I told, right, same funda which we had for BCl3 and BS3, same thing here we have. CCl4 carbon can handle chlorine, 4 chlorines around it, but it cannot handle 4 OH molecules around it. Correct? So except CCl4, other tetrachlorides experience hydrolysis with water, where all these chlorine molecules are replaced with OH molecules. These are OH molecules. Right? Hope you understand this. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.